I'm going to present to you my pet functional programming language with a rather eccentric type system by starting with prologue. This is a prologue snippet. Well, it's just a query, really. And he asked the system to give me a prime number, and it tells me, yeah, okay, so 2 is a prime, and 3 is a prime. So we have queries in a logic programming language, and we don't have that in functional programming languages. Now, what is the type here of this query variable? Apparently, the query generates results, and apparently these are numbers. So the type of the results is int, okay, integer. Now, what if we try to integrate queries into a functional language, as we have seen on Monday? What types do we get? That is not so clear, because now we have a query which can return no results at all, or maybe one result, or maybe lots of results. And whereas it's easy in logic programming languages to type that, because we don't have to deal with explicitly destructuring sets and so on. That's not so clear in a functional programming language. But really, when we want to lift the backtracking and the non-determinism of a logic programming paradigm into the functional language itself, then apparently the sets are gone too. So again, x here is of type int, not of type set of int. But what really is this strange query exists as prime? Can we actually implement it in functional terms? In functional terms, of course, this is just a backtracking computation, which is a computation which can have multiple values, which can branch at some points. And here I have, by hand waving, basically, inserted some kind of representation of this functional structure. So x is a 2, or it is a 3, or it is a 5, which is, so this or thing is the choice points in the backtracking system. Okay, so we can build a programming language that does that. That's not all that unusual. One can do that. It's probably been done many times before. We just start with some atomic values at the top, and then we have the choice points, which I call fusions, which will become clear why shortly. Now I've also introduced into my programming language pairs, which is rather obvious, and patterns for pattern matching. And since this is a functional programming language, of course, we also need anonymous functions. And I also permit unrestricted fixed points. Now, there are also these comprehension things which I wanted to be talking about. So, now we want to type this stuff. But how do the types look like? What do the types look like? It might be interesting to have the type system operate in the same terms as the object language. That is usually something desirable. Also, in this case, it would be doubly desirable because if we could use this language to describe types, then we could use logic programming to describe types. Queries, for example. So we could have queries as types. Now we already have these weird plus things, these weird sums in there. What can we do with those? Well, we are basically collections. We can just stitch together values and we get bigger values. So why not just use them as a replacement for types, for sets? So we could just define, well, the type of integers that might just be the computation that produces all the integers. A query, basically. But what do we have then? Okay, so as I said, a backtracking computation just is a simple type, not a set type. So the computation that produces all the prime numbers just has this type, this int type. And also, of course, the computation that produces all the integers also has a type of all the integers. Of int. So this is just int itself, right? Int has type int. Now that's rather strange, isn't it? So a set is contained in itself. Usually that leads to contradictions. But in this case, what we're doing, we're just doing subtyping. If we consider all these things as sets, then this is just a subset relation. So everything is a type. Every value we can write, every value we can generate, every term we can write in this programming language, we can use as a type. And its inhabitants are simply the subtypes. Okay. So I've got some examples. These are just atomic values. You can regard them as strings. They look like Lisp quoted symbols. That's what they are. The symbol hi is its own type, of course, because everything is its own type. Okay, subtyping. I mean, if typing is just subtyping, then for every value we have we as a type of we. That makes sense. True as type true or false, it also makes sense. True and false, that's just the Boolean type. You can write it like this. No need to build this into the language. Well, pairs. What about pairs? Well, if you have pairs, and we actually use subtyping for typing, then it would be sensible to have the typing actually behave the same as subtyping on types of pairs, because a pair is just a type of pairs, and that means it must behave like the subtyping of products. So we have this. We also have the reverse, by the way. So 1, 2 plus 3 is also type 1, 2 plus 1, 2, 3. So what can we do with it? With a strange system? Well, we can try to emulate algebraic data types with the natural numbers. By simply applying a fixed point operation and doing some kind of sum, which generates all the fixed points, all the naturals, which generates all the naturals. We have now a computation which generates all the naturals, and that is the type of naturals. This is the result. Just as you would expect. We start with a 0 case and then build larger numbers by adding successor tags on top of that. Note that we do not need any special provision for data constructors. They just follow naturally from having some kind of atomic objects. We just use these suck and 0 atoms. Lists, no problem, we can do that. Polymorphic even. We simply define a function which takes a type argument and we generate in the usual way a type of lists of that element type. Right? So that's what we get. We even get dependent types for free. It basically falls out by itself. since we don't distinguish between types and values anymore because they're just the same thing, there is no distinction between a polymorphic type that takes a type as an argument or a value. There is no difference there. This is the standard classical vector example. The vectors of with elements of type A and length, well, 0 or successive n. And also, interestingly, this type, it's its own type, right? This is the identity function and its own type too. This is already a dependent type. This is probably the simplest functional dependent type that you've ever seen. Because now the result type depends on the input, right? If 2 is type 2, but not type 3. Okay, polymorphism, that's just the same as independent types. It just falls out naturally, just as it does in ACTA and things like that. But note, there is one thing here that is important to note. That is that A and F, you would have to distinguish between them if this wasn't this language. You would have to distinguish between A, which is a type parameter, and F, which is a runtime value parameter. The system doesn't distinguish between those. Okay. So that's basically the quick rundown of the language. And so what have we gained by doing all this? Well, we have a system that is very simple, has no need for the distinction between types and values, is rather powerful. The type system can model dependent types, polymorphic types, and, well, one can use it to write programs. In particular, to write queries. You can embed queries quite naturally.